almost any structure, even a large and expensive one, can be at risk from corrosion. When these expansion joints were designed, not enough consideration was given to drainage. And, even in summer, surface water will still be contaminated with salts, used to prevent the formation of winter ice. There is always a need to protect against likely corrosion, and often the extra cost at the design stage would be small. A simple cover would have greatly reduced maintenance. Like the bridge, cars are attacked by water and road salts, and most rust out before they wear out. More complete protection could be provided, but at additional cost. And most people who buy a new car sell it before corrosion becomes their problem. Conversely, because failure can lead to catastrophe, in the design of aircraft, much more attention has been given to avoiding corrosion. If corrosion can be anticipated, both in and out of service, at the design stage, then ideas for protection which are economically viable can be included. Generally, for a short life, low initial cost, and frequent maintenance may be economical, as in the car. However, for a longer working life, it may be better to pay a higher initial cost with more protection from corrosion and then less frequent maintenance. There comes a time when overall it is more economical to pay a higher cost to begin with and then less expensive maintenance. So, when the lifespan has been decided, the optimum design will be the one that gives the lowest total cost. That is, capital outlay plus maintenance charges. Once the economics have been established and a choice made, the full technical details of design can proceed. In the prevention of corrosion, a first consideration should be the effects of shape, as for example, on drainage in storage vessels. If an outlet pipe is above the bottom of the tank, residual liquid may in time become more concentrated and corrode the interior. Complete drainage is achieved by correct choice of shape in the design. Different outlet faults are commonly found. With incomplete drainage, many liquids may concentrate from evaporation and become more corrosive. However, some liquids become dilute when left in a nearly empty tank. Sulfuric acid, when concentrated, does not attack iron, but becomes aggressive when diluted. Complete drainage will avoid corrosion. Corrosion can occur both on the inside and on the outside of a vessel. Exterior shape can also prevent corrosion. When lifted well off ground, the underside is accessible for maintenance and painting. Good design of legs eliminates trapped water in crevices and facilitates cleaning. Inside, an outlet pipe at the bottom and machined flush gives the essential complete drainage. As we have seen, if the outlet is not flush, corrosion can occur. The liquid left between process cycles concentrated by evaporation then attacked the weld and caused pitting of the bottom of the vessel. A minor fault in design can shut down a large and costly operation through corrosion. Acidic gases can shorten the life of a steel exhaust system. In 6 months, silencers like this were perforated from condensed acid and needed replacement. The system is contained in a thin sheet steel box. To quieten the engine, the hot gases pass into tubes lined with sound-absorbing material. With the train in motion, the cold outside air condensed acids on the metal and allowed rapid corrosion. The problem was overcome by creating a double skin and then putting insulation material in the cavity. A problem solved by design. Designers are familiar with the stress-raising property of notches, and where notches are unavoidable, as in a screw thread, appropriate allowance can be made in the strength of the material. But in a corrosive environment, at a stress at which it would normally be safe, a material can fail. This is stress-assisted corrosion cracking. For example, a section from a high-pressure pipe suspected of being liable to stress corrosion cracking was tested. A sharp notch was cut into it, and then a fine crack induced. The end of the crack is marked with a scored line. This crack acts as a severe stress raiser. Put in tension, the opening of the crack is measured with a transducer. In a non-corrosive atmosphere, the crack opens slightly as the load is applied, but does not grow any further. A similar specimen is then surrounded by a cell which is to contain the corrosive medium circulated by a pump. When the corrosive is introduced, the crack starts to grow. Eventually, assisted by corrosion, the specimen breaks under a load it had previously withstood. Another problem of stress-assisted corrosion, with an unexpected solution, was the failure of axles on trains often working in a humid atmosphere. When the wheels were taken off, fretting corrosion, due to minute movements between the wheel and its axle, had produced a corrosion scar. The stress-raising crack associated with the scar can be found by electromagnetic detection. The fluctuating stresses during operation in the corrosive atmosphere had caused the crack to propagate, and then the axle had to be replaced after a relatively short life. The remedy lay not in changing the material or trying to exclude the atmosphere, but in design. By simply machining a groove in the axle, the high stress moved there and away from the area of the wheel, and the fretting corrosion was reduced. There have been no cracks after 1 million kilometers. When two plates are bolted together, they form crevices. If one of the plates is metal, in a moist environment, lack of dissolved oxygen in the crevice with higher oxygen outside sets up an electrochemical cell, producing acids. There is crevice corrosion. If the plates are totally immersed in a mildly corrosive medium, the conditions inside the crevice are again different from those outside, and again, crevice corrosion will occur. The attack on outside surfaces is negligible. The designer can avoid crevice corrosion by preventing the penetration of moisture. This can be done by complete sealing, with mastics, coatings, or by welding. Anywhere moisture collects, as is possible inside a car door, crevice corrosion can occur in seams. The crevice acts as a moisture trap. remaining wet from capillary action when the rest goes dry. This is aggravated by road salts. Bad body corrosion not only looks unsightly, but will greatly reduce protection in a crash. Seawater is very aggressive to metals. It will even attack stainless steels, especially if a crevice is formed. This is a problem in pumps, where in idle periods the stagnant conditions may allow crevices to corrode. It can be overcome either by flushing with fresh water before shutdown, or by using different materials. Threads, too, form crevices, and stainless steel bolts can suffer attack in seawater. The remedy is the use of especially resistant metals. In a chemical plant, a more sophisticated example of crevice corrosion occurred in titanium-lined vessels. Titanium is normally highly corrosion resistant, but in this case a crevice was formed at the flange, where severe corrosion then occurred. At breakdown, the cost of the delay in production was considerable. The solution to the problem has been a more precise fit of the flanges to eliminate the crevice. The improved flange shows no corrosion. At the design stage, the cost of the remedy would have been trivial. Metals which corrode slowly will often be protected by the corrosion products left on their surface, so that if a liquid is moving slowly, there will be an acceptably low rate of corrosion. But rapid flow or turbulence may remove the protective layer and permit severe corrosion. This is termed erosion corrosion. It can occur in any situation which increases liquid flow sufficiently. In a seawater pipe, as a valve closed, the rush of water increased and removed the protective oxide layers. Erosion corrosion occurred. The remedy for the designer is to use either a larger valve or a more corrosion-resistant material. A brass filter was similarly corroded because of the speed of flow of seawater. The solution was to use a plastic-coated material inert to seawater, which incidentally was cheaper than brass. Interference with normal flow can lead to turbulence. For example, a protrusion into the stream. A wrongly sized packing gasket caused turbulence and eventually erosion corrosion. In industry, erosion corrosion causes many problems in cooling water systems, and most can be overcome by design. With many heat exchangers, where seawater is used as a coolant, in spite of filters, inlet pipes are seen at maintenance to be partially blocked with debris. This can affect flow and give turbulence, which in turn can increase erosion corrosion. This can also occur on the outside of tubes. An incorrectly designed baffle to deflect hot products led to these streaming through the narrow gap between tube and support. In cooling tubes, erosion corrosion does not usually occur along the whole length of the tube, but at the inlet where turbulence occurs. So, for economy, protective inserts are used, which, when eroded, may be replaced at shutdown. The period between maintenance is doubled, and with new inserts, the life of tubes prolonged for many years. We have seen that when metals are placed in an electrolyte, such as seawater or wet earth, each of them may corrode. However, when the two dissimilar metals are brought into direct contact with each other and immersed in an electrolyte, the corrosion of the steel will be accelerated. But at the same time, the copper will have been protected. This reaction is turned to advantage in cathodic protection, used, for example, on underground pipes and ships. On its own, the steel hull would corrode in seawater where paint had been damaged. So, zinc blocks are fitted in good electrical contact with the steel. The steel is protected and the zinc corrodes. With zinc blocks fitted in the right places, the hull remains intact as long as the zinc is replaced regularly. In an electrolyte, metals have an order in which, in electrical contact, they will become either the anode or cathode to each other. This is the electrochemical series. It also includes certain non-metals, such as carbon. When in contact with copper, a metal higher in the series, iron, is corroded. Similarly, when iron is in contact with aluminium, lower in the series, the iron is protected and the aluminium corrodes. In choosing associated metals, the designer must be aware that an incorrect choice can lead to destructive corrosion. Aluminium was chosen to give a light yet strong bridge without the need for painting. But the aluminium girders were fastened by steel rivets. This proved to be an incorrect decision. For where moisture collects, bimetallic corrosion is destroying the bridge. So strengthening has been needed. Bolts of a compatible material, or plated bolts, should have been chosen. The steel shell of a heat exchanger not only has to withstand normal corrosion, but also aggressive bimetallic corrosion from coupling with the copper tubes. This is overcome by placing the steel in direct contact with zinc, lower in the electrochemical series, so that both steel and copper are protected at the expense of the zinc. Similarly, on end plates, the zinc is sacrificial and replaced at normal maintenance periods. Where possible, further protection comes from an insulating coat of paint. In all industry, some 60% of failures which occur from corrosion are due to errors in design. The designer should bear in mind the effect upon corrosion of shape, the problems where failure comes from stress-assisted corrosion, the need to avoid crevices which lead to corrosion, the flow of liquids, and corrosion by erosion. And bimetallic corrosion from incompatible metals. When all these factors are considered in relation to the economics, the lifespan, and the practical use, then there can be prevention of corrosion. prevention of corrosion at the drawing board by good design.